Welcome back. This lecture is about setting up our own neural network code. And we are going to use this one in particular in project number 2. So the topic today is simply just to go through many of the details which are needed in order to set up our own neural network code. Next week, we are going to discuss in more detail some further technicalities, both connected with the backpropagation algorithm. We are going to look at further applications, in particular with applications to neural networks to the solution of differential equations, and then we're moving into convolutional neural networks and recurrent neural networks, and we're also going to look, as an aside, we are going to look at how we can use TensorFlow and APIs like Keras, which normally makes it much easier to set up our own neural network. But the main aim today is to simply go through the basic details which are needed in order for us to be able to set up our own code for a neural network. So if we scroll down, the topics which we went through yesterday in the previous lecture was a review of the backpropagation algorithm. So there are 4 equations which we need to set up, and these 4 equations provide us with a way of computing the gradient of the cost function. And this is something which you will have to set up in project number 1. So in this particular case, the program which we are going to develop is a program which has only one hidden layer. In project number 2, you are actually tasked with setting up a more general program where you can have more than just one hidden layer. But for pedagogical reasons, we are just going to go through the setup of a neural network, a feed-forward neural network with just one hidden layer. So the typical operations which we will need to do is 1, to define this quantity which we defined as a delta, which is now proportional with the derivative of the activation function which we have chosen. So in the lecture notes we have been using either f or sigma as a way to identify the activation function, and c is a cost function or loss function which we want to optimize with respect to the parameters, which in our case are the weights and the biases of a neural network. Then we can compute using backpropagation, which, as we discussed in the previous lecture, is the same as the reverse mode of the automatic differentiation algorithm. We would trace ourselves back to the different layers, and the algorithm for updating this parameter delta j, which enters the definition of the gradients, which we train in a backward mode, step by step, till we reach the input layer. So we would have an updating algorithm where we update the weights and the biases for each single hidden layer. In our case, we're just going to have one hidden layer. So when we are setting up a multi-layer perceptron model, or a feed-forward neural network, as it is always also called, we are going to look at the data set, which is a generalization of the binary problem. And this is a data set which is called the MNIST database, which contains handwritten numbers, and we're going to use a classification algorithm with a neural network to recognize and train a network which can then recognize handwritten numbers. So in binary classification problems with 2 classes, we will typically use the logistic sig or the sigmoid function as a probability that a particular input is in class 0 and 1. And this is possible because the logistic function takes any input from real numbers and inputs a number between 0 and 1. And then you can decide if it's less than 0.5, you output the label as the output is then labeled as a 0. And if it is larger than 0.5, you would then output 1 as your result. And this would be the typical function which you would put on the final output layer. So for an input from the hidden layer, the probability that this input is in class 0 or 1 is just given by what this function would reproduce for you. And you let theta represent the unknown weights and biases to be adjusted by our equations. And this is something which we also discussed in connection with logistic regression. Then we need to define the cost function in that particular case. And in this particular case, when we looked at logistic regression, if we go back to the logistic regression slides, we remember that we defined what was called the cross entropy, which was based on the log of the product of the individual probabilities. And then we ended up with a function here where we can now have the cases with y or y equal to 0. And then we have 1 minus y of I equal to 0, which is then supposed to represent the output y of I equal to 1. And this is often written as the sum over the individual contributions, which are sometimes called the loss function, but there's often a kind of confusion with the description of the function we want to optimize. Sometimes people call this the loss function. We have systematically tried to call this the cost function, which is then the sum of the individual loss functions. So this equality, this last equality, means that we can interpret our cost function as a sum over the different loss function for each point in a data set. So when we are dealing with a multi-class data set, it's pretty common then to actually rewrite the outputs in terms of bit strings. So we would typically have since we have this MNIST data set which contains 1,000 numbers from 0 to 9, we could then use a bit string to represent, let's say, number 5 here in terms of 0, 0, 0 up to 1. So that would be number 5 here. And then we would have the slot for 6, 7, 8, and 9 here. And similarly, you see here number 1 would then be recognized in terms of the bit string, which gives us 0 here, that's a slot for 0, 1 here for the slot for 1, and 0 else. This is often called a so-called one-hot vector in the literature. The function which we then would use when we are dealing with a classification problem with more than just a binary problem is something which is called the softmax function. Now, for those of you who come from physics or astrophysics or chemistry, you may have heard about the Boltzmann distribution. And what you see here is simply just a adaptation of the Boltzmann distribution to a multi-class problem, and where each class now has a given probability, and we scale that with a normalization factor, which is the sum of all the possible events which we have. So if you're familiar with something which is called the Boltzmann distribution, this is actually the Boltzmann distribution tailored to a classification problem. It's nothing more than that. So that means that the likelihood function for this type of categories or class classifier is then going to be the product of all the events and then multiplied with the product of all the different classes here. And with this P of y here is simply going to be represented as the probability of one specific event. And this is the function which we would then adapt to the classification problem. And this is the function which we would use in the final output layer. Now, when in project number 2, where we are also going to deal with a regression problem, then in the regression problem, as we mentioned in the previous lecture, in the regression problem, the output from the last output layer, which we then compare with the targets, is simply just going to be given by the numbers which the last layer produces. And it's not going to be modulated by any type of activation functions. So this will be now the activation function for the output layer. And since we have 10 numbers, we are going to have 10 nodes in the output layer. In the hidden layer, we can have as many nodes as we want. And these hidden nodes connect then with the input layer. And in our case, we are going to have pictures which are scaled down to 8 times 8 pixels, which means that we have 64 input variables for each image. These are then multiplied with a weight matrix and fed into the different hidden nodes. And then the hidden nodes produce an output which are modulated by an activation function, which in this case could be a sigmoid function, it could be a tanh function, it could be a ReLU function, or any type of activation function which we are looking at. And in project number 2, you're also going to play around with different types of activation functions. Now, if we now scroll down here, you will also see that the function which we want to optimize now is going to be the so-called negative log likelihood. And it's pretty similar to what we did with logistic regression, except that now we have to include the different categories or classes of events. If you look at the binary problem, which is a little bit simpler, and in order to gain some kind of intuition, it can actually be useful to do that. And in project number 2, the classification problem we're looking at is a data set which now contains only 2 outputs. And these outputs are either a benign tumor or a malignant tumor. So that's a typical example of a binary problem. So for project number 2, what you need to do is to set up the logistic function for 2 possibilities. And this is something which you will then plug in as the activation function for your output layer. So just keep in mind that depending on the type of classification problem or regression type of problem, you may have different activation functions in the output layer. So in project number 2, we are going to simply use, for instance, the logistic regression function, or just a sigmoid function as it's normally called. And in the examples here, we are going to look at a typical classification problem with more than 2 classes. And then we need something which, like this softmax function, which is a way to modulate the output from the output layer, which we then compare with the targets. So if we now look at the mathematics which we went through in the previous lecture and the lectures from last week, what we need then is would be what we have in the output layer or a given hidden layer. So we would then have the output, which we would typically label with a Y, and this is going to be compared with the targets. So in our case, this L which you see here is now this lowercase l is going to be replaced by the L in the output layer, which is our final layer. And this is the cost function where we now compare the results which we have with the targets which we want to reproduce. So the cost function for the classification problem for the binary problem is then going to include the targets here and then the outputs from the neural network which we have defined. And then the derivatives follow what we did during the lectures last week. And it's easy to calculate this quantity here. So we would need the derivative with respect to the outputs from the last hidden layer or the last layer. If we do the softmax function, we then have to set up the derivative of the function which we have opted for as an output function, which in our case is a softmax function. And the softmax function in this particular case is now given by the Boltzmann factor, which you have here, and divided by the sum over all the probabilities for each single class here. So as I mentioned earlier, the softmax function is nothing but a generalization of what's called the Boltzmann distribution for a given set of classes or categories. And the derivative in that case, and this is something which I invite you to look a little bit at, is now a derivative which is slightly different from the one which we had from the sigmoid function, which then included only a binary classification problem. And in that specific case, the derivative of this function here doesn't contain the Kronecker delta which we see here. So the main difference between the sigmoid function or the logistic function and the softmax function is that now the derivative is given in terms of the function itself, and then there's a Kronecker delta minus the function value. While when we take the sigmoid function, what we have then is just 1 minus the function itself. Now keep in mind that these derivatives, they change from activation function to activation function. So if you have a ReLO function, this expression here will obviously change. And it is convenient when you're now setting up your program to actually try to make a list of possible activation functions, because then the derivatives will actually take different expressions. So in the binary model, this simply reproduces to having I equal to j, and it's just 1 here. Now, the thing we need to do now, as we discussed yesterday as well, when we are setting up a neural network, is that we need to collect and pre-process the data. So for us, this is in project number 2, when we look at the classification problem, this has always been done. This has already been done due to the facilities which we have with scikit-learn, where the data set is already prepared for a classification problem. And that means that the collection and pre-processing of the data is something which we don't need to think of. Then we need to define a model and architecture, as we discussed yesterday. So the architecture will then be defined by the type of activation functions which we're using. We need to define the number of hidden layers. We need to define the number of hidden nodes. And these defines, in our case, the specific model, in the same way as we defined a model in linear regression, for example, using a polynomial of a certain degree. In our case, the model is now defined by the architecture of the neural network. Then we also needed to define the cost function. We need to find the optimizers, and then we need to train the model, and this is done by the feed forward and the back propagation algorithm. And then we need to evaluate the model performance on test data. So that means that we need to set aside some data which are not included in the training. And finally, we have hyperparameters which we need to deal with. So we need to find a regularization recipe. So the data set which we are going to use in order to define our specific application is now the MNIST dataset. And this dataset actually contains more than 70,000 images. And these images, the standard size is actually given by 28 times 28 pixels. And each one's a label from 0 to 9. Now, in these lectures, we are going to use the reduced dataset, which is actually a compressed set of images, which contains only roughly 1,800 images, and they are given by 8 times 8 pixels. And the main reason for using this specific dataset is simply that else it would take way too much time to demonstrate and run the codes during these lectures here. So the way we are going to represent the data, and this is something we want you to think about when you're writing your program, we need to set up a design feature matrix, which typically includes the number of inputs and the number of features. So in the cancer dataset, we are going to have something like 30 features, and then we will have input data of something like 500, 600 patients. So that means that your design matrix in that specific case is now given by a matrix which contains roughly 500, 600 data points, and then it's going to have something like 30 features. So it will be something like a 500 times 30 of dimension for the dimensionality of the design matrix. Now, when we are looking at the images here, we are going to flatten it, because we are going to have 64 inputs for each image. And each row here would then represent an input in the case of a handwritten digit, and each column represents a feature, which in this case would be a pixel. And the correct answers, also known as labels or targets, are then represented as a one-dimensional array of integers. So you could have the numbers 5, 3, 1, etc. So if we are now looking at the images here, we would have then each row to be represented by an input, which is a handwritten digit, so that's an image. So this would be the number of images, and we would have something like 1,800 images. And the features would be the pixels. So that means that we would have 8 times 8, which means 64 features. So just to give you an example, if you wish to bring this down to a simpler case, if you want to make a prediction about the body mass index for a given person, you could think of you having the inputs for 5 people. So the first feature is the height of the person, and the second feature, which is the second column, would then be the weight of that specific person. And then you have a formula for calculating the body mass index in terms of the height and the weight of the person, and that means that your output is given here, and this is the body mass index. And since each input in an image is a two-dimensional matrix, what we are doing then is actually we're going to flatten the image, or in a Python NumPy-like language, we are going to unravel the two-dimensional matrix into a one-dimensional array. And then we're going to turn the data into a design feature matrix. So that means in a certain sense we lose the spatial information in an image, such as locality and translational invariance. And more complicated architectures, such as convolutional neural networks, they can take advantage of such information. And this is normally used when we are analyzing images. And we are coming back to that when we are going to discuss convolutional neural networks. So the first thing we are going to do now, and as we said, if we scroll up a little bit and we look at the first point here, which is collecting and pre-processing our data, in our specific case, the data has already been set up by us, by scikit-learn for us, and there is actually no need to go through the data analysis where we look at the data set, prepare the data set, and prepare it as the input variable so we can read it into our programs. In our specific case now, what we have is a data set which is already ready for us, and we simply need to when we use scikit-learn, we simply include this package which is called dataset, and then we just load the digits here. And then we say that the inputs are given by the digit images, and the labels are just given by the digit targets. And then we can extract the number of inputs. We can find a way to reshape the number of inputs, so we flatten it out. And then we can also define a specific image which we want to display here. So if you now look at this preparation or pre-processing of the data, what we are going to get then is something which looks like a number. So this will be randomly selected inputs, and if you use some imagination, you can see that these are images with 8 times 8 pixels, and these are images which are a little bit blurred. So with some imagination, you can think of this as number 8, and this is number 7, this is number 3. So all the data have been labeled, which means that the only thing we need to do when we are training the model is actually to simply use the labels here, and with these images we can then train a neural network. So in this specific case, what you see now is that the inputs, the way they are read in from scikit-learn, they contain now the number of images, and then we have the pixel width and the pixel height, and we have the number of labels are going to be given by 1797, and then we have the inputs, the design matrix now, which is rewritten in terms of the number of inputs and the number of features, which are 64. So we have 8 times 8 pixels, and that gives us 64 features. This defines the design matrix for us. And these are the entries which we wish to train. And then, as we've done before, we want now to set up the data set so we can do the training. And we will typically reserve 80% of the data set for training and 20% for testing. And again, what we're going to use then is to simply use the functionality of scikit-learn. Alternatively, if you wish to, you can define your own train test split if you want to. But normally what we would do is to recommend using these kind of functionality which is included with scikit-learn. And This means that if we run it, you will see now that for the training of the model, we have something like 1400 images, and then we have something like 360 images for training. Now, the model which we are going to set up and the architecture is going to be defined by a simple feed-forward neural network, which will consist of an input layer. It's going to contain a single hidden layer, and it's going to contain an output layer. And the activation function of each neuron is a weighted sum of inputs, which is passed through an activation function. In case of the simple perceptron model, we would simply have a function which receives as input this variable z, which then contains a vector of the weights and the input variables, which would be an AI here, which would be the input coming from the output of the previous layer. So f would now be the activation function, and this a of I represents an input from a neuron I in the preceding layer. And in our specific case, since we have, if we in this case have a simple perceptron model with no hidden layer, this a of I is just going to be the input x of I. So the simple perceptron model, as we discussed earlier, is a model which will not do a very good job if we have something which is beyond linear. And that's why we will typically start with setting up a hidden layer, at least one hidden layer. So the layers which we're going to set up contains now an input layer, and so each image has 64 pixels. So that means we have an input layer of 64 neurons. So for each image. And then if we look at the hidden layer, and now we are defining the architecture of the hidden layers. So we have one hidden layer, and we could now place 50 neurons. So that means that each neuron in the hidden layer is connected to 64 input nodes or input neurons. And that means that the weights we have to define in the optimization part is given by 64 times 50. So we would have 3,200 unknown parameters which we need to train. And if you think back to project number 1, where we just had some few parameters, this means that this is going to be a much more complicated multi-dimensional optimization problem. And then we have the output layer. So if we were looking at a binary classification problem, then we would just need one single neuron in the output layer, and that single neuron could just output 0 and 1. So in the case of the cancer data, this is exactly what we would do. So you could take the Heaviside function, you could use the sigmoid function, or you could use a function which you think is more appropriate. Now, when we now come to the classification problem, then it's common to use this softmax function. And in our case, we're going to have a class here, and then we have the inputs to that specific node. And each node then represents the neurons. They present a given, they're given by a certain activation input, and they're modulated by the activation function, which is now the softmax function. So the neurons outputs the probability of being in class J, giving an input from the hidden layers. And this input is A, and this is weighted by the weights here. So these weights are then given by the components of a weight matrix multiplied with the output from the previous layer, and then we add to this the bias, which is meant to compensate for possibilities that the weights are all 0, which means that the training will actually stop if we didn't have a bias parameter. And this bias is actually a parameter itself, and we would treat that on the same footing as the weights. So we need to now set up in the backpropagation algorithm a way to train the weights and the biases. So each neuron in the output layer is then connected to 50 inputs from the hidden layer. So that means that in total we have 500 weights to the output layer from the hidden layer. So the number of parameters, when we now add the biases, so since we have 10 neurons in the hidden layer, we would have 10 bias variables. So plus 500, it means that the output layer has 510 parameters which we need to define. And if we go back to the hidden layer, we would have 3,200 weights, and since we have 50 nodes, we would have 50 bias variables for each single node. That means that we have 3,250 weights and biases for the hidden layer, plus 510 weights and biases in the output layer. So that means in total we end up with 3,760 parameters which we need to tune. Now, there's a topic which we need to discuss a little bit later, and which is a very delicate one, and that's how we initialize the weights and the biases. So we normally would not initialize them to 0, because then there would be no feed-forward pass. And we also have to make sure that the biases and the weights are not too large, because that can easily lead to exploding gradients when we are training the network. So it's typical and it's standard to initialize the weights and the biases with some small values distributed around 0, and they are normally drawn from a normal distribution, not a uniform distribution. You could use a uniform distribution also. And if you set all weights to 0, that means that the neurons would just give the same output, and that makes the network useless. So adding a bias thus to the value of the weighted sum of inputs allows the neural network to represent a greater range of values. Without it, any input with a value 0 would be mapped to 0, and that's before being passed through the activation function. And the bias unit has an output of 1, and a weight of each neuron j is now given simply by this function z or j here. So we have the weights multiplied with the input from the previous layer. In our case, the previous layer, in case of the hidden layer, is just going to be the input layer. So that's going to be the variables x, which we have defined earlier as the number of pixels of a given image. And the bias weights, they are often initialized to 0, but typically one will set it to a small value like 0.01. And in many cases, what many practitioners do is that they do actually set the weights and the biases according to the normal distribution, and then distribute it around 0 and initialize everything with small values. So when we are now setting up the neural network, we need first to initialize it. So we have the number of inputs and number of features, which is now given by the shape of the design matrix which we have. We need to define the number of hidden neurons. So if we have more hidden layers, we would then have to set up the number of hidden neurons for every given hidden layer. And then finally, for the output layer, we need to set up how many output nodes we want to have. In our case, we have 10 handwritten numbers, so that means we need to have 10 categories. And that means 10 output nodes in the output layer. And then we are now initializing the hidden weights. And this is given by a random distribution. And we have the number of features and the number of hidden neurons. That's the dimensionality of the weight matrix. And then we have the hidden neurons, which then define the hidden bias. And then we simply add a +1 here. So we just fix that one to a fixed value, but then the network is actually training the biases and the weights. And that the network will actually change in the backpropagation algorithm. It's going to change the values of the biases as well. And then we need to do the same thing for the output weights and the output biases. And now you see that the dimensionality of that matrix is given by the number of hidden neurons times the number of categories. And as we said, if we have 50 hidden neurons and 10 categories, this is a matrix which has 500 elements. And in this specific case, the number of features are the number of pixels, which are 64. So we would have 64 times 50 for the hidden weights. And that is 3,200 matrix elements, which we need to train. So this would be the initialization part of the setup of the problem. So we've done the pre-processing of the data here, as we did here. So we pre-processed the inputs. We've decided the dimensionalities of the network through the architecture. And then we need to initialize everything. So this is the first step. And next, we need now to do the feed forward pass. So in the feed forward pass, what we have now, since we have only one hidden layer and one output layer, plus the input layer, so we would then have in the hidden layer, we would have an input to each node, which is modulated with the weights, multiplied with the input variables. And this runs through all the hidden nodes in the hidden layer. And this is then passed to the activation function. So every node in the hidden layer produces now an output. And this is then passed, this output here is then passed to the output layer. And in our case, the output layer has only 10 nodes. And these 10 nodes take now an input, z of j of L, uppercase letter L. And we have the weights here. In total, we have 500 with the kind of architectures which we have opted for. We have 10 biases. And these variables, z of j, enter then the softmax function, and they produce an output. And this is the output which we are going to compare with the targets. Now, for project number 2, you would need to replace this one with, for example, the logistic function or the sigmoid function, because you're going to have a binary classification problem. In the case of a regression problem, the output from the output layer is simply given by the number z. So that means we do not modulate the output from a given output layer in terms of a function like the softmax function or the logistic regression function or the sigmoid function. So that means that the output in a regression problem, when you are fitting a specific function or some data, then that one is simply going to be given by z. So a of j of L is going to be z of j of L. Then we need to set up the different operations in the feed forward pass. So we need to think of the matrix multiplications. So remember now that the dimensionality of the design matrix, which contains our input data, is given by the number of input variables. In our case, we have something like, for training, 1400 images, and then with number of features are the pixels, which are 64. So then this needs to be multiplied with the first hidden layer weight matrix. So that is going to have number of features times number of hidden nodes. So that means we need to perform a matrix multiplication here in terms of the inputs and the number of hidden nodes which we have here. So that means that the input z to the activation function is now given by the matrix here which we have multiplied with the matrix w plus the bias vectors here. And that's the input which we feed in to the activation function. And in our case, this could be a sigmoid function if we want to, or any other ones of the activation functions. And if we now specialize to the sigmoid function, you would now see that this function here, f, is now replaced by the sigmoid function which we plugged in here. And then when we have done the feed forward pass through the hidden layer, we get an input to the softmax function, and that produces our output. So if you look at the feed forward pass, it contains now one, it takes in the design matrix with a data set, and then it performs a matrix multiplication with x and the hidden weights, and it adds the bias vector. And then we feed this one into the sigmoid function, and we produce the output from the hidden layer. So a underscore h is the output from the hidden layer. And this is now passed to the output layer. And so you see now that what we have is these inputs, which are the outputs from the hidden layer, are then multiplied with the weights, which connect the hidden layer and the output layer. And then we have the output bias. And then what I'm calculating now is the exponential term, which enters the calculation of the softmax function. So it takes in z of 0, and then it simply calculates the scaled probabilities, which is a adaptation of the Boltzmann factor in the case of a classification problem. And this now returns the probabilities. And then the probabilities are then defined by this feed-forward function here. So this is the feed-forward pass. And then we simply print here the probabilities for the different images which we have. And then we can make a prediction. So the prediction which is made now is our probabilities given in terms of this feed-forward network. And then it simply returns these probabilities here. And that would be the probability which we have now when we are done with the feed-forward pass here. And you can see now a printout and a prediction for an image. So we will make a prediction for an image which is 8, whereas the correct label is actually 6. So this is the first feed-forward pass. And clearly, when we do the first feed-forward pass, there is no guarantee that we will actually predict things correctly. And here you can see the probabilities for the different images which we have here. And you see that the largest probability is this one. So that is, when we sum up, by the way, this is normalized to 1. And you see now that the largest probability is the one which corresponds to number 8 here. And that's the one which we predict. All the other ones are basically 0. Now, the next thing we need to do now is to add a cost function. And in these multi-class problems, it's often common to actually treat each integer label as a so-called one-hot vector, which we encode as a bit string. So that's a pretty standard way of doing that. And 10 is then the number of classes in the MNIST data set here. And if we now are optimizing the function here, what we need now is to think of the back propagation pass. So we saw now that the probabilities here, which we obtained with the first feed-forward pass, where we have simply initialized the weights and the biases, so there's no training, there's no optimization in it. Then we make a wrong prediction of that specific image, which we just picked randomly among the 1400 something images which we have here. So what we need to do now is to start including gradient descent. We need to set up the backpropagation algorithm. So we have already discussed how to optimize these functions, and we can do this in many different ways. We can do a stochastic gradient descent. We can do a stochastic gradient descent with momentum, as we discussed in week 39. We can do a stochastic gradient descent with momentum and adaptive learning rates via the Adagrad algorithm. We can do the same thing. We can replace the Adagrad algorithm with the root mean square propagation. And we can also replace the root mean square propagation with the algorithm for ADAM, which is an adaptive momentum-based method. And these are all ways by which we can perform the optimization. And the number of batches and the number of epochs and the number of data points which we have in each batch is something which then we have to look at as parameters. And we have already discussed this in the gradient descent approaches. And this is actually part of project number 2, where you have to write a gradient descent method. In the beginning, we are training that against a simpler function, but we are going to use the same gradient descent algorithm in the optimization of a classification problem as well. Another thing we need to think of, as we discussed earlier, is actually the regularization term which we add. So that adds a new parameter to our cost function. And typically now this is done by optimizing a term which includes only the weights, not the biases. And that means that we need to run over all the matrix elements of the weight matrices. And we have then a tuning parameter lambda, which we also call a regularization parameter. So the problem which we have then is that in our network we would typically have, for this specific case, we would have something like 3,200 roughly weights, and a similar one 500 in the output layer. So the 10 here is the number of biases, and 50 is the number of biases as well. In the hidden layer and the output layer we have 10 biases. So the gradient have to be calculated for each one of these parameters, except that when we do the regularization part, that contains only a shrinkage parameter on the weights and not on the biases. So now we have set up the basic features of a neural network. So we have the cost function and optimization part. We need to decide which kind of optimization we want to do. And then we have decided upon the architecture or the model of the network. And then we simply have to perform the matrix-matrix multiplications in the gradient descent. And remember now that for the output layer, for this specific case, the derivative of the function which we have opted for, the cost function, is simply the target minus the output from the last hidden layer, which is the output layer. And then we need to calculate the gradients for the weights, which are simply given by the outputs multiplied with the outputs from the previous hidden layer multiplied with the parameter delta. And then similarly we need the same thing for the biases, and we can then set up the calculation of the derivatives. And in this specific case, what we need to do now is to set up the feed-forward pass, which we did earlier, and then we have the back propagation part. So in the back propagation part now we calculate the error in the output. So we have these probabilities, which are the outputs, minus y here, which is now the target we're dealing with. We calculate now this error function, this delta, which we had. We set this up, and then we calculate the gradients for the weights and the gradients for the biases, and this is all for the output layer. And then this is now fed into, using the the back propagation algorithm, this is now fed into the hidden layer, and this then returns the output weights and gradients for the output layer, the same with the bias, and then we have the hidden weights gradient and the hidden bias gradient. And with that, we have updated the weights and the biases, as you can see here. So we start with a regularization parameter, lambda. We start with a training or learning rate, which eta, which we put to 10 to the minus 2 here. We calculate the gradients with the back propagation piece. We regularize the terms. So this is now the regularization term. And then we compute the output weights, the new output biases, the new hidden weights, and the new hidden biases. So this would be one iteration. So one iteration has a feed-forward pass, and then it has a back propagation part. So that's one iteration. And if we run now this calculation here, you will now see that the accuracy on the training data, the old one, was 0.14. So that was the first feed-forward pass. And then the new accuracy is now given by 0.1. Actually, we would like to have 1 here. And this is not very impressive. So when we are now setting up the calculations, what we end up doing is that we're actually going to perform a calculation where we now run over many learning rates, and we are going to set up different regularization parameters. Now, with a neural network being set up, the next pass which we need to do now is actually to try to improve performance. And one of the standard ways by doing this is actually to set up an array of learning rate variables and also the regularization parameters. And then we're going to tune these parameters in order to find the best possible accuracy in our case, or mean squared error if you're doing a typical regression problem. So we, when we have implemented a gradient descent, a stochastic gradient descent, for example, and we have included the regularizers and we have included the weights, we would typically call this, as we mentioned earlier, we call this feed forward plus the backward pass with a mini batch, an iteration, and a full training period going through the entire data set, we would typically call that an epoch. If this does not improve network performance, you may want to consider changing the network architecture. You could add more neurons, you could add more hidden layers, and so on. There's actually a nice video by Andrew Ng which goes through some of these considerations. The network now, when we're writing the code, so keep also in mind that the codes which we display in these lecture notes, we try to keep them as simple as possible, which means that we are not going to bring in too many fancy things. But here we can now write a class which we could call a neural network, where we simply define the input data, the output data, the number of hidden neurons, all the parameters which are needed. We can define the number of epochs, we can define the batch size, we define the learning rate, and then we have the regularization parameter lambda. And then we can then, if we now go through it, we would have the create biases and weights. So this is where we initialize the output and the hidden layers, the parameters for these. We have the feed forward pass. We have the feed forward output piece, which takes in these terms and then calculates the probabilities and returns them. So we would have the back propagation part, where we now simply update the gradients. And in this specific case, you can see now the gradient updating algorithm, which you see in here. We are calculating the gradients, and then we have the updating of the gradients, which you see down here. And by this, we can make predictions, and we have the final probabilities, which in our case is the final result from the output layer. And then we can now run over, in the training here, we can now run over the number of epochs, and then the number of iterations, which then defines, in this specific case, is defined by the number of batches which we have. So essentially what you see here is the way you would now set up the training of a neural network. And then we need to evaluate the performance on test data. And the simplest way to evaluate the performance is actually to calculate the accuracy. And we simply collect the number of times we classify correctly, and we divide by the number of data points which we have. So an accuracy of 1 means that we have a perfect reproduction of the data. And you can see now here, where we are now setting up our neural network, we define 100 epochs, we have a batch size of 100. These become parameters, keep that in mind. And then we call our class neural network, and then we perform the training. And then with the training, we then make a prediction, and the prediction is simply us evaluating the accuracy score, this quantity which you see here. And then the accuracy score is simply calculated, as you can see here. Alternatively, you can use the functionality which you have in scikit-learn. So the accuracy score is just us comparing the prediction we make with the data which we have. And if that, in the test case, remember that we are now comparing with the test data, and then we simply sum up the cases where we have a hit and divide by the total number of data points which we have. And that returns the accuracy. And that's the kind of score which we are going to look at. Now, when you do this now and do a specific run, this is actually not so bad. So now we have done the training with a given number of epochs and a batch size here. Next thing is actually to adjust the hyperparameters. And when we adjust the hyperparameters, we are now setting up a grid of values. And note now that we are not doing a refined optimization of the parameters. We are simply now running through it without any kind of adaptive step size for the learning rate. There is no momentum in the gradient descent method. It's a stochastic gradient descent, but there is no momentum gradient descent. There is no adaptation of the learning rate. So we just plug in these values and we compute the accuracy which we get with these specific learning rates and these specific regularization parameters lambda. And then what you do now, we do it simply just the grid search, and we tabulate the values, and we pick the values of eta and lambda which give the best accuracy score. And when we run the calculations now, what you would see is something like this when is running. When we have a very small learning rate and a small value of lambda, you see now that the accuracy is not impressive. But when we increase the learning rate, we see now that this value of 10 to the minus 5 for the learning rate was not very realistic. And if we just keep on moving, you can see now that when we increase the learning rate, we get a learning rate of 10 to the minus 4 here with a lambda value of 10. We are getting closer to 100 or 1, which is the ideal value. When we increase the learning rate, this clearly seems to be giving a better accuracy score on the test set. So if we scroll down here, you can see now that we are reaching something which looks better. So the human accuracy, so that means you taking random humans and showing them these images, the accuracy is something like 98%. And we are going to see now that our neural network is actually going to behave more or less like the way a human would be. Now, when you look at all these numbers, it can often be a little bit confusing, and it's something which we normally recommend is to use a package like Seaborn, which is actually a nice way of displaying a heat map, and you can use it in connection with matplotlib as well, and this gives a much nicer display of the data. So if you now take a look here, you would now see something which looks like this. So the given learning rates which we have here, so this is on the training, and you can see now that these eta parameters you have here on the y-axis, so this would be the third learning rate. The first one is 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, and this is 10 to the minus 2. And then we have a hyperparameter lambda, which doesn't seem to change too much, these results. But you see now that for a certain number of lambda values, you have basically a perfect training score. So that means that picking a lambda corresponding to 10 to the minus 2, an eta, a learning rate 10 to the minus 2, between 10 to the minus 2 and 10 to the minus 3 seems to be giving the best possible results here for the training. And now, when we've done that, we can look at the test accuracy. And in our case, we are getting pretty close to what is a normal human achievement, which is 0.98, 0.97. So our network with a learning rate, which is 10 to the minus 2, and a hyperparameter lambda, which is now 10 to the minus 1, gives us something which is pretty close. And this kind of grid search is normally what we end up doing in these neural network calculations or in this type of optimization problems. And then we could then try to make some kind of grid search which optimizes the parameters lambda and eta. But alternatively, we can add a scale learning rate by using these adaptive methods like AdaGrad, root mean square propagation, or ADAM, or any other type of scale learning rate where we have a scheduler for the learning rate. We could add momentum, which will speed up the iterative process. So these are all things which we can use to refine what we have here. Now, we can then also use scikit-learn. And scikit-learn is a library which hasn't specialized into deep learning method, but it contains a multi-layer perceptron model. And it contains two options, one which is the regression case and one which is the classification problem. So, and we have been doing a classification problem, and in that case what you would need to define then is the typical activation functions you want to deal with, a logistic activation function. You have to define the number of hidden layers, the number of hidden neurons, you need to define the number of epochs, the learning rate eta, and we are then running the same kind of calculation now, but where we call the MLP classifier instead of the function which we have defined. And then we fit the network. We, for the values of I and j, the etas, the learning rates, and the lambda parameters, we then produce an accuracy score, and in scikit-learn this will be the function which is called score, and that gives us the accuracy score. So we could run the network here as well, and this contains some additional optimizations which we have not included in our network. So if we move on here, you will see much of the same results which we had, and we can now, when we've done the calculation, you will also see that we may need to increase the number of iterations in the stochastic optimizers, because you can see now that there's a warning that the method hasn't converged yet. So when we're done here, we can now repeat the same visualization which we did earlier, and now you see that scikit-learn is actually doing a little bit better than our simple neural network. So this contains additional optimizations with perhaps momentum. It may use RMS prop, ADAGRAD, and so on. And you can see now that the span of values of the learning rate and also the parameter lambda, the regularization parameter, is a little bit larger. So we actually move from 10 to the minus 4 to 10 to the minus 2, which seems to be giving a pretty good result on the training. And then if you look at the test accuracy, you will see now that we have a test accuracy which is close to 100, which means it fares better than actually a human. Now we can use these type of calculations back on the problem which we discussed 2 weeks ago, where we look at this XOR, or the OR, and the AND gates. So these are simple systems which now just have two inputs. And if we now do that and look at these specific cases, we could have X1, which is 0, 0, 1, 1. So these are the bits which we have. And this will be the values of X2. And here we have the outputs. So this will be a typical, the first one is an OR gate. So if we have 0, 0, it spits out 0. 0, 1 gives 1. 1, 0, 1, and 1, 1 gives 1. And then we can have the AND gate and the XOR gate. And as we discussed last time, we would now have a input or design matrix, input matrix, or the design matrix, where we have X1 in the first column, X2 in the second column. And then we have the different outputs, which would be 0, 1, 1 if this is an XOR gate, 0, 0, 1 for the AND gate, and 0, 1, 1, 1 for the OR gate. So this defines our input parameters and output parameters. And then we can set up the neural network as we have done before, and then we could do something like a feed-forward pass and make the predictions. And we would have a design matrix, which is given by the matrix above. And then we have the different outputs which we are looking at here. So we have only two categories. We have two hidden neurons, and we have two features. And then you can make the weights normally distributed. As we did before, we can calculate. So this is with only one hidden layer. And then we can look at our predictions here. So, and if we do that, you will now see that the predictions for the case of an OR gate and an AND gate is actually doing decently. But then for the case of the XOR gate, it's actually giving a pretty poor prediction. But this was only the feed forward pass with randomly assigned weights. If we now repeat the same thing with scikit-learn, we would then define the different outputs. We need to define the number of inputs and number of features, which are given by the shape of the design matrix, as before. We set up the number of hidden neurons. We set up the number of categories, the number of features we want to deal with, because these are the number of categories which we want. So we have either 0 and 1. And then we will set up the parameters eta. We will set up the parameters lambda, so the learning rate and the lambda parameters. And then we will simply run through here. And if we do that, when we do the calculations, you would now see that the accuracy score for, let's say, if we now look at the XOR gate. So if we take that specific case, and now we want to compare this with the XOR gate, you would see now that for the training parameters here, for specific variables, lambda and learning rates, we are actually getting the correct prediction which we should get. So the if we now scroll down here, you will see that we have the 0.75 and 0.25. So this will be a case where we have either 0 and 1. So the setting up the learning rates and the parameter lambda, you will now find a region here where we actually do have a perfect hit with 1 and 1 here, so where we classify correctly. So depending on the parameter lambda, we have now a neural network with one hidden layer, which now reproduces for this learning rate, which is equal to 10 to the minus 1, and the parameter lambda, which goes from 10 to the minus 3 to 10 to the minus 2. It gives us now a correct prediction for the XOR gate. All the other ones fail in one way or the other one. But you see now that a neural network with one hidden layer, with a given hyperparameters lambda and a given learning rate eta, we are able to classify correctly. So when we get an accuracy score which is equal to 1, then we have done a perfect job here. And this is a very simple implementation using scikit-learn. We could alternatively have used the function which we have described. And I invite you to actually try that out. Now, one of the things which we are going to do next week is to look at building a neural network with TensorFlow and Keras. And we're also going to discuss many of the pros and cons of neural networks. But this now stops the lecture on building your own neural network. And this is something which is highly relevant for project number 2. And next week, we are going to look in more details into applications of TensorFlow and Keras and how we can easily make calculations of neural networks with any type of hidden layers and any type of stochastic optimization methods, learning rate adaptations, and all the other features which we need when we are setting up a neural network. And then we're also going to look at applications to the solution of differential equations. But this stops the present lecture.